Okay, I think this will probably be the last video or close to it of the section here on derivative concepts. And this one we're going to be looking at several real world, or at least 2 or 3 real world situations, and we're going to see how from these situations we can know something about the derivative, or how, if we know something about the derivative, what it tells us about the situation. So this is putting these things in context. Okay? So here is the problem for you. Let V represent the value of a certain stock and T represent time. Suppose you know that at the present time dV over dt equals 0 and d2, the second derivative of V with respect to time, is less than 0. So the first derivative is 0, the second derivative is less than 0. Now, by the way, you don't know this with stocks. If you knew this kind of information with stocks, you would be a super millionaire, a billionaire, because you could make lots and lots of money on the stock market. But suppose these things are true. What does this say about the value of the stock? Now, suppose you're interested in selling maybe in the near future. Should you sell now, or do you want to hang on for a little bit? What do you think? And how do you know? So see if you can explain that in terms of these derivatives. Explain it in terms of the stock. When you think you have this figured out, come back. Press pause now. Now, since the derivative is 0, the first derivative of the value, that means the value function has a horizontal tangent line. And since the second derivative is not 0, that's an extremum. Specifically, the second derivative is negative, so it's concave. The derivative, the original graph of V is concave down. So what we have here is a concave down graph. Okay, something like this, but it has a horizontal tangent line. So where are we? We're right here at a maximum. So the graph is at a local maximum, and so, well, that's a perfect time to sell. Okay? Buy low, sell highs when you make your money, right? So you're as high as you're going to get, at least locally. Now, eventually this may turn around and come back up, but at least locally, this is the best you can get. So what you sell now, sell it now. If you wanted to buy it again, buy it a few days later when it's down here, and you'll have made some money. Okay, let's try another one. Okay, this one has some multiple parts, so let's start with this one. Suppose W is the weight of a stack of papers in an open container, and T represents time. A lighted match is thrown into the stack at time T equals 0. So what's going to happen? Well, the papers are going to catch on fire. What's going to happen to the weight of those papers? What is the sign of W prime of T during the time that the stack is burning, and how do you know that's true? So you're going to want to answer these questions in the context of the original problem. Okay, see if you can figure that out. Come back when you're ready, when you have a solution. Press pause now. Well, when we ask about the sign of a derivative, what we're asking about is whether the original function is increasing or decreasing. Now, when the thing is burning, when the paper is burning, the weight of the stack is going down. So the function W is decreasing, and so W prime must be negative. All right, here's another question, same situation. So in this scenario, how can you determine from W prime of T that the fire is no longer burning? What if somebody just gave you a graph of W prime of T? Could you point to the spot that the fire quit burning? Think about that. Come back when you're ready. Press pause. Okay, well, one way you can find is if the fire quits burning, the weight of the stack of the papers is no longer changing. Therefore, the weight function becomes constant, and the derivative function is 0. So when we see that W prime of T hits 0, we know that the fire went out. So if it goes down to 0, then it will actually stay 0 for a while. But the point where it hits 0 on the derivative function, that's when you know the fire is no longer burning. All right, now here's a situation here. Let's suppose that the fire starts large, but then decreases in vigor, less vigorous over a certain time interval. What can we say about W prime of t and W double prime of t? This may require a little more thought. Let's think about this a while. Come back when you think you've got it worked out. Press pause now. Well, if the fire's going, okay, then we know W prime is negative because the weight's going down. But let's see what happens. So we know that the original graph of W here, okay, let's say we graph W here. W is decreasing, but what happens? It starts large, so it's decreasing really fast, but then it doesn't decrease as fast as much anymore in the future. What is that? Well, that's decreasing concave up. So that means W prime is negative and W prime is decreasing. And W double prime, the original graph is concave up, W double prime is positive. I believe that's what I said there. Okay? Now let's try a completely different scenario. Okay? As of my recording this, the Super Bowl has just happened, and they have a lot of commercials at the Super Bowl. So suppose that for 2 weeks after the Super Bowl, the total number N of beverages sold by a particular company is related to the number X of times the company's commercial is played during the Super Bowl. What's meant by the function N of X? Okay, or in particular, what is N of 12 equals 2,468,050? What does that mean? Okay, see if you can explain that. Press pause till you get it figured out, and then come back. Okay, so 12 is an input, which is an X value, which is the times the commercial is played, and N is the output, or the Y value, or the number of beverages sold. So this says if and when they play their commercial 12 times during the Super Bowl, then they're going to sell 2,468,050 beverages for this 2-week period. What are the units of N prime of X? Now, by the way, I'm kind of fudging a little bit here. Since the number of commercials is actually a discrete value, it's 0, 1, 2, 3, 4, 5, it's a whole number. The derivative technically wouldn't exist then, because you can't have, to have the derivative you need a continuous function. But let's say we're modeling this with a continuous function. So we're modeling this function with a continuous function, even though in reality the x has to be a whole number. So if you could take the derivative, what would the units be? Okay, see if you can figure that out, and then come back when you got it worked out. Press pause now. Now, in general, units of the derivative are always fractional units. They're output units over input units. So it's units of N divided by units of X. Now, N is measured in number of beverages, right? And X is in terms of number of commercials. So it's beverages per commercial play. So it's number of beverages sold per times the commercial is played. And that units alone helps you see that this actually is a rate of change in this context. Okay, let's try another. What's the sign of N prime of X, and how do you know? Is N prime positive, negative, or 0? And how would you know that? See if you can answer that one, and then come back when you're done. Press pause now. Well, when I'm asking about the sign of N prime, I'm asking about whether N is increasing, decreasing, or constant. So let's think of it that way. If we increase X, will N go up, down, or stay the same? Well, X is how many times they play the commercial. Well, what they're hoping is that if they increase the times the commercial is played, they're going to somehow increase their sales of the beverage. It would have to be an extremely bad commercial to make it go to decrease the beverages, and it might not have any real effect, but it's probably going to have some positive effect where the n is going to increase whenever you increase the x. So that's an increasing function. N is an increasing function of x, and so that makes its derivative have a positive sign. So n prime of x is positive. So let's suppose that n prime of x, n prime of 12, let's say, is 2,150. Now what would that mean? Think about that one a bit. What does n prime of 12 equals 2,150 mean? When you get that worked out, come back and let's check your work. Press pause now. Well, let's think about this a minute. This says that the derivative is at 12. So we're talking about the point where we're playing the commercial 12 times during the Super Bowl. That there are 2,150 is the rate of change. So it's an instantaneous rate of change. So that's approximately the marginal increase in the beverages sold. So what that means is, at least it's approximately how much the number of sales go up from selling one, or from playing that commercial one additional time. So from going from 12 to 13, it will result in approximately 2,150 more beverages sold. So with that, we should be able to estimate, say, n at 12. Well, we have n at 12. We've got n at 12. Let's review what that is up here. So you might want to write that down. N at 12 is 2,468,050. And we have n prime is 2,150 when x is 12. Okay? So use that to estimate n of 13. And by the way, we could also estimate n of 11 as well. Figure this out and come back when you got it done. Press pause now. Okay, well, n of 13 is about the same thing as n of 12 plus n prime of 12. It's what we had, about 2,468,050. And what we're adding on is at least approximately the same amount as the derivative, which is 2,150. So it's going to mean that we're going to get approximately 2,470,200 beverages sold during the 2-week period when the commercial is played 13 times. If we wanted to do n of 11, we do n of 12 minus n prime of 12. So we take this number here, this big number here, and we would subtract our derivative. Now let's further suppose that n double prime is negative. What can you say about this estimate that we came up here? Here's our estimate, 2,470,200. What can you say about that estimate, and how do you know? Okay, that's a little bit more challenging. Let me let you stop and think about that one a bit, and then come back when you're ready. Press pause now. Okay, so let's think about what we've got here. We've got an increasing function. Okay, we've got a so the derivative is positive, and the second derivative is negative, so that's concave down. So we got our function of n looks like this, increasing concave down. Well, if you look at the tangent line, it's going to be above this. So the true amount that goes up is actually going to be less than the amount of the derivative. If delta x is 1, then this value right here is the derivative. It's how much the derivative is how much the tangent line goes up, whereas this distance here in red is the actual amount the function goes up. So what do we know? We know our estimate's a bit high, right? Probably not much, just a little bit, maybe by 2 or 3 or 4 beverages. But our estimate is going to be a little high this way. Now, if this function was linear to begin with, then this estimate would be right on. But since it's concave down, this estimate's a little high. If it was increasing and concave down, this is too high. Increasing and concave up, then it'd be the other way around. So the actual value is close to this number, but a little bit less. Okay, I think that's going to do it for this set of problems. Hopefully that gives you several different example problems that you can reinforce and practice with on the topics from this particular playlist. And hopefully now that you finish this playlist, you're in pretty good shape of understanding what's really going on with a derivative. More in the next couple of playlists about derivative. As the next playlist we'll talk about the derivative shortcut rules, and so we'll come up with a lot of algebraic manipulation of formulas in the next unit. And then the unit after that, we'll come back to more problems like these here and other problems where we can apply concepts and formulas from derivatives and use them to solve some real-world problems. So we've got at least a couple more playlists dealing with derivatives.